Good evening, everyone. Welcome to Physics by RN. I'm this side RN Mehra, okay, and I'm taking the Quantum Mechanics in 3 dimension lecture series. We are taking this session because this topic is extremely important for gate physics, net physics, JEST, and so on. So far, I have taken 3 classes, okay. In one class, I discuss the basics of quantum mechanics, how you can think in terms of quantum mechanics and so on. What are states, what are operators. In second class, I actually started solving hydrogen atom problem. Hydrogen atom problem is a very basis of quantum mechanics in 3D, from which you can understand each and every aspect about the whatever you need about the quantum mechanics in 3 dimensions. So what we saw is that while we are solving the Schrodinger equation for hydrogen atom, we can divide our solution into 2 parts. Number one, radial part of the solution, and number two, the spherical harmonic part of the solution. Okay, so since we can divide in these 2 parts, so in second lecture we discuss more about the spherical harmonic part. Spherical harmonic part actually tells us about the angular momentum. It gives us an information more about the angular momentum of an hydrogen atom or any system in which we are dealing in the 3 dimensions. So then we move to the third session, in which we discuss the radial part of the solution. What we mainly focused about was, if solution has been given to us, then how we can actually talk about the quantum numbers and so on, instead of deriving the solutions itself, because that is not required for us. We don't want to derive the solutions. Instead, if solutions are given to us, we should know how to analyze them, how to find different properties through those solutions, and how to tell what quantum numbers our hydrogen atom or any system R is having. Okay, so now we will move to the next step. Okay, now we will talk more in detail about the angular momentums. There are two angular momentum. Number one angular momentum is orbital angular momentum, and number two is spin angular momentum. Today's class we will be discussing more about orbital angular momentum. Most probably it will not be covered in one session. Tomorrow also we will be doing orbital itself. And then once we have a very good grip over orbital angular momentum, similar analysis is done for spin angular momentum. It's a quite simple idea. Okay, so let's just begin with. So orbital angular momentum, which we usually describe by a vector L vector. Okay, can any one of you tell me, in classical mechanics, what does L means? In classical mechanics, forget about quantum mechanics.
Angular momentum.
Yeah, but which angular momentum? It's orbital angular momentum, but what does it means?
Corresponding to angle phi.
No, what? No. See, if I asking you what does mass means, then it's a very simple question. What does angular momentum means? Why it comes and why? What is its significance in the physical world?
Related to rotation, and when any body rotates about its own axis,
No, when it's
we
rotate about
decide an axis.
no, when it's rotate about its own axis, then we don't actually say orbital angular momentum. Then we say spin. Isn't it?
Means it's rotating about any other body or any other point.
Okay, so momentum word comes from the picture that momentum and inertia are quite related. Okay, so whenever something is in motion, it achieves some sort of momentum, physical quantity, which we call it as momentum. Now, what does this momentum, why we call it as momentum? Newton's second law gives an interpretation that momentum is equivalent to force, because force is dp by dt. If something has a momentum, then it means it can do the work, it have an energy, and it can also apply the force. So classical energy is associated with the momentum. Okay, number two, angular word here means the momentum which the body is achieving because of the rotational motion, not because of the linear motion. If it is linear motion, then we call it as linear momentum. And the word orbital means the rotation is we are talking about is one body is rotating about some other body, or maybe both of those bodies are moving around the center of mass of those two bodies. So these three words combined gives us the orbital angular momentum. Now in quantum mechanics, not exactly, we can't say that electron is revolving around nucleus or something like that, but analogy to whatever we are discussing is quite analogy to orbital angular momentum, because classical world we can easily imagine. So we are creating an analogy, but we are not saying that exactly electron is revolving around the nucleus. That's not a correct interpretation, but let's say. So for now, let's assume that electron is revolving around the nucleus, and whatever the angular momentum it is having is called orbital angular momentum. So now orbital angular momentum, you can define it in terms of three things: Lx, Ly, and Lz. Okay. Basically, in quantum mechanics, we deals with the four quantities while we are discussing orbital angular momentum: Lx, Ly, Lz, and L square. These four properties, these four physical parameters will tell you everything you need about the orbital angular momentum. So I do understand why we need Lx, Ly, and Lz. Why we need L square? Can anyone guess?
So maybe
Very simple.
because Alex can take negative values.
No, it can take an let it take L negative values. What's the problem? So if you have px, yeah,
L square is the magnitude of,
huh?
sir, therefore, sir, square root comes on L. To remove that square root, I think we take the
No,
square of
no,
L.
no, 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 no. That is mathematical. We know how to find square roots, na? Mathematically, we can find. So what is p square in classical mechanics? What is p square? P square by 2m. What is that?
Kinetic energy.
So,
Kinetic energy.
so what is L square by 2i? See, p square by 2m, in if you do a rotational analogy, it will become L square by 2i. I is moment of inertia, isn't it?
Yes, sir.
So what is the L square by 2i
Yes.
then?
Additional
Same.
kind.
Rotational kinetic energy, na? So whatever energy our system is having because of the angular momentum. I just said momentum inherently means that it can do work and it has some energy. Okay, and it can exert force. So we also need to discuss what is energy it is acquiring. For that reason, L square is very important. Okay, so that you should keep in mind. Whenever I say L square, the very much thing that should come to your mind is energy. Whenever, if we can do something on L square, it means we can do that on energy. Okay, so that you should remember. Lx, Ly, you will know that why these are important, because it's quite simple that any vector has three components and we should have an information about those three components. Now let's move to next step. Commutation relations. Okay, this is very important. In quantum mechanics, commutation related relations are extremely important. It tells you the compatibility between the two operators. I will go in this detail, but let's see what is commutator first and then go into the physics of commutation. And it's a very famous question of quantum mechanics. So can anyone tell me what is commutator in quantum mechanics? You should know that you are an MSc student. Hmm? What is
Mathematically, T minus BA.
So
Sir,
all of you know that matrix commutation, you all know. If you have two matrices A, B, and if it is equals to BA, then A and B commute with each other. You all must have heard this, even a BSc student, right? So number one thing that you should remember is commutation relations are always defined in with each other in only for operators. And what does operator signifies in quantum mechanics? Hmm? Very simple. What does operator signifies in quantum mechanics?
Measurement of some physical quantity.
Physical observables. Okay, so we always define commutation relation between the two operators, let's say A and B. How we define it? We define it A, B, minus BA. What does it mean actually? It means if I now tell me whatever is on the right hand side, is it also an operator?
Yes, sir.
It is also an operator. Okay. So this operator, when acting on some state F, any state F. Okay. So what will happen is A will act on F first and then B will act. Similarly, in this situation, B will act first and then A will act. Okay. So if this comes out to be 0, let's say this comes out to be 0, then what does it signify? Then it tells you that if A is acting first on F and then B is acting, or maybe B is acting first on F and then A is acting, you are getting the same answer. Only then you will get a 0 answer, because if this and this will be equal, only then you will get an equal answer. So your system does not matter. It does not matter that which of these is happening. Either A is acting first or B is acting first. Now this may seem quite mathematical, but now let's come back to uncertainty principle, Heisenberg uncertainty principle. What happens is that, can you measure both X and P together? According to uncertainty principle, can you measure X and P together with a complete precision?
No, sir.
No.
It means if I measure momentum, it disturbs the information about the position. And if I measure the position first, it disturbs the information about momentum. So then do you think, if let's say I want to measure the position of my system F. Okay. So what I do is, first I measure the momentum and then I measure the position. This is case 1. And then case 2 is, first I measure the position and then I measure the momentum. So do you think answer will be same in both the cases?
No, sir.
Why? Because in first case, when momentum was observed on F, then its information about the position got changed. But in second case, in the very first step, we measured the position. So in second case, we got the correct information about the position, but in first case, we got the wrong information. So did every one of you got this, what I am saying?
Yes, sir.
Yes, right.
So if two operators actually commute, means gives the both same information, doesn't matter if you operate A first or B first, then it means they both are compatible with each other. What do you mean by compatible? Means measurement of one operator does not disturb the information about the second operator. There are many such operators. For example, if you are actually measuring Lx and then you measure Ly, doesn't matter. You can do that. Measurement of Lx won't change the Ly. Okay, and we will see that how. Okay, similarly, if you measure Lz, you can measure then Ly. Similarly, if you measure the position along X, then you can again go and measure the position along Y, because the measurement of position along X won't change the position along the Y. So this is something which we should know. I think Lx and Ly information I gave it wrong. No, if you measure Lx, then you have to keep in mind, come to that. So, but you should now know that one thing, if they commute, then it means they are compatible. So commute means compatible. Compatible means you can measure both of them at the same time with the complete precision. So everyone got an exact idea about this?
Yes, sir.
Commute means compatible. This is a very basic rule of quantum mechanics. Okay. Now, if you know what is now operators, then what are our commutators? Then let's come to our quantities which we want to discuss. So what are those quantities? Lx, Ly, Lz, and L square. So if you see Lx and Ly, if you commute them, it will give you iota h cut Lz. Formulas you should remember by very, very much importantly, these you should remember. I will drive also one of them, because you should know how to actually solve the commutators. But You won't have a time to derive this in the exam, so please remember these formulas. If you get Lx into Ly, if you commute them, you get iota h cut Lz. So what does it tells you? Can you measure Lx and Ly together or not?
No, not with
No, sir.
accuracy.
No, because they are not commuting, they are not giving 0. It means if you measure Ly first and Lx then, or Lx first and then Ly, both of them are not equal. That is why we are not getting answer 0. So that's why we can't measure Lx and Ly together. It means the measurement of Lx will disturb the information about Ly and vice versa. Okay, so I didn't mention them in notes. So let's together mention them so that we can actually have a very good summary point also. So if two operators commute, let's write that if two operators commute, what does it means? They both are, tell me.
Compatible.
Compatible. That is, we can measure both of them simultaneously. Now, can anyone tell me, is this a correct, is it a complete information? Should I stop it simultaneously or there should be something else I should write? Is it complete information or not?
But I think simultaneously we cannot measure any, because if we want to do the position measurement, then after only we can do the energy measurement. Like
No,
because position and
you can measure simultaneously. No, you can measure simultaneously. It's not like that. For example, let's say I say you measure kinetic energy and p square together. Can't you do that? What you need to do? You only measure p square and then divide by 2m. It will also give you kinetic energy. So then kinetic energy and p square will be compatible. Understand? So you can measure both. But simultaneously, it's not a complete word. We can measure any two operators simultaneously. But the problem is it won't give you a precise answers. It won't give you the correct answers. So what we should write is we can measure both of them simultaneously with 100% precision. What does it mean? That is measurement of one observable, measurement of, please write these down, it's very important, of one operator do not disturb measurement of second operator. Second operator. Now, there is one more information which I want to add here. Okay, because you should, this is very important. Now, what does it says? If A cap into B cap commutation relation is 0, the both operators share same eigenstates. So how many of you are actually able to understand this sentence? It's very, I don't expect you to, but do you? The both operators share same eigenstates.
yes, sir.
Yes. So why they should have a same eigenstates?
Sir, because they can be simultaneously eigenized.
Okay. Now let me bring you all back to the how we do the measurement in quantum mechanics. Very important. Okay, so let's say you are having a system. This is your system. It is in state phi. Okay, it is in state phi. This state phi is a superposition of this state. A phi chi1 plus B chi 2. Sorry, B chi 2. Now chi1 and chi2 are the eigenstates of let's say operator A. Now, if I do the measurement of A on this state phi, do you get both A and B value, or do you get any one of them?
Both A and B.
No, you get any one of them. I discussed that yesterday. Okay. You get any one of them. Sometimes you can only decide what is the probability of finding phi 1 and what is the probability of finding phi 2. But at a one time you will get only one. It's similar to you have a coin in which is in a superposition state of head plus tail. Okay, you have a coin which is in superposition state of head and tail, and both have 50% probability. So okay, so 50% of the time you will get head, 50% of time you will get tail, but in one measurement you will only get either head or tail. So do you all agree till here?
Yes, sir.
Yes.
So if you are in such state A phi 1 plus B phi 2, okay, and let's say A is energy operator, H cut operator. So if you get phi 1, it means you get energy E1. If you get phi 2, it means you get energy E2. So what is the probability of getting energy E1? I already told you it is A square by A square plus B square. And what is the probability that you get E2? B square by A square plus B square. So do you all remember this? This A and B only tells you about the probabilities. Okay.
Yes.
Okay. So if you all understood, then it means if you operate this A operator on your this superposition state, you get any one of them. So you get some value. Let's say let's replace this by h cup so that you have a better understanding. So you get E1 into phi 1. Okay, because you got the energy E1 and now your state is phi 1. All of you understood till here? Or it is also possible that you operated on this and you got E2 phi 2. Understood? समझे यहाँ तक? It's very complicated things. That is why I'm slowing it down. So do you all got it till here?
Yes, sir.
These are the two possibilities.
Yes, sir.
Everyone else, do you got that idea or not? Something new you have seen here?
Yes, sir.
बताओ भाई, जल्दी बताओ.
Yes, sir.
Okay, so now let's see it from the perspective of B vector, B operator. Now let's say B operator is a momentum operator. And now this state can also be written in terms of eigenstates of P. Okay, if you can write any state in terms of eigenstates of A, then you can write this state in terms of eigenstates of P also. So what do we do? It is alpha chi1 plus beta chi2. So the two possibilities now is you operate P on phi and you get P1 chi1 or you get P2 chi2. Understood? समझे भाई, जल्दी बोलो.
Yes, sir.
ठीक है? So now if I'm saying H and P are compatible, if I'm saying this, okay, then what I'm saying, let's say after I can measure both of them at the same time. I measured both of them. After the measurement, let's say I measured H cut and H cap and P cap at the same time. Now after the measurement, they have to be in one state, na? It's not possible, na? They are also in phi 1 and chi 1. So in order to have both of them in the same state, it is compulsory na that their eigenstate must be equal. समझे अब? Otherwise, your H cap operator is saying it should be in state phi 1, but your P cap operator is saying it should be in state chi 1. And you can measure both of them at the same time. So what will be the state after the measurement? Phi 1 or chi 1? So in order to resolve this conflict, phi1 and chi1 should be equal. So eigenstates of the two compatible operators should be same. So do you agree?
Yes, sir.
सबको समझ आया? So these two statements भूलोगे तो नहीं? What does the compatibility of the two operators mean physically? Is the main idea which we should take away from this. So if you got this, just wait. My screen is a little bit frozen. Okay. So any question till here?
Sir.
Yeah.
Sir, if we measure something using some operator,
Mm-hmm.
then it will have some eigenstate.
Yes.
Some particular eigenstate. Similarly, like for momentum we measure, we'll get some eigenstate. But those states will be different, no, for different operators.
No, but if you are measuring both of them at the same time, at exact same time, now what will be the eigenstate afterwards?
Yes, sir, I got your point. But if I'm measuring, suppose 3 or 4 observables simultaneously,
then if you can measure 3 and 4 at the same time, then all 3 or 4 will share the same set of eigenstates. Two matrices can have the same eigenstates, na? Isn't it?
Yes, sir.
So that's I'm saying. If two operators are compatible, if you can measure them at the same time, it means their eigenstates must be same. Okay. In general, if they are not compatible, you can't measure them at the same time. Then their eigenstates will be different. That's what I'm saying.
Okay, sir.
Right?
Yes.
सब समझ गए? कोई क्वेश्चन यहां तक? Okay. So if there is no question, you all got an idea. So now let's see how you actually can find Lx, Ly commutation relation is equals to iota h cut Lz. So first, number one way to remember is if your thing is going clockwise, Lx, then Ly and Lz, then you put no negative sign. So Lx, Ly give you iota h cut Lz. Ly, Lz give you iota h cut Lz. Lz, Lx give you iota h cut Ly. But if you go anti-clockwise, means Ly, Lx will give you minus iota h cut Lz. So this is number one way to remember. Now, if I'm saying commutation relation between L square and Lx is 0, what does it mean? Can you measure L square and Lx at the same time? बताओ भाई, can you measure L square and Lx at the same time?
Yes, sir.
I want to confuse you. Yes or no?
We can, because they are commuting, they are compatible.
100%. Whatever information we have, it's correct. Definitely correct. So if I can measure L square and Lx at the same time, can I measure L square and Ly at the same time?
Yes.
So I can measure L square and Lx at the same time. I can measure L square and Ly at the same time. So can I measure L square, Lx and Ly at the same time?
No, sir.
Yes.
No, because these two are compatible. These two are compatible, but Lx and Ly are not compatible. So in order to measure all three together, all three should be compatible with each other. You understand? Got an idea?
Yes, sir.
Okay, perfect.
Sir,
Yes.
then how are we able to measure L square and L means Lx, Ly, Lz? They like form L na, Lx I cap, Ly j cap, Lz k cap. Then L square and L we are able to measure together. Then we should be able to measure Lx and Ly as well. So let's
No,
say Lz.
see, I just told you L square by 2I gives you kinetic energy. So you are in one thing you are doing is you are measuring the angular momentum along one direction Lx, and also you are measuring the total energy. So that actually gives you information about L square and Lx. But if you now try to measure the angular momentum along x-axis and y-axis also, it changes. Now it disturbs the system. So you can't do that. But you can do L square and Lx at the same time, or L square and Ly at the same time. But if you try to do L square, Lx and Ly all three at the same time, it's also a problem. Why? Because Lx and Ly are not compatible. Okay.
Yes, Bhaiya.
Okay. So now let's move forward. These commutation relation you should know. So if L square into Lx is 0, L square into Ly is 0, L square comma Lz is 0, then L square comma L vector should also be 0, isn't it? It's very simple. Na? L vector can be written as Lx, Ly and Lz. So commutator relation also splits up and it gives you 0. So these relations you should actually remember. Okay, so now let's move and let's find out how you actually find these commutation relations. So whenever someone asks you commutation relation, find the commutation relation. Number one thing you should know is commutation relation is itself an operator. Okay, because we just discussed it is also an operator. So operate it on some function, on some let's in this line you can see now it is operating. So Lx Ly f minus Ly Lx f. So what does the first term means? Ly will operate first and then Lx will operate. Similarly, what the second term means? Lx will operate first and then Ly will operate. But mathematically, what are these Lx, Ly? So you know angular momentum is R cross P. Okay. And if you open it up, you get this y pz minus z py x cap. Till here, everything fine?
Yes, sir.
Yes.
Now I convert it to operator form. What is an operator form of pz? Minus iota h cut, curly by curly z. Right? Similarly, py minus iota h cut, curly by curly y. So I just put that value into it here. So you get some three operators like this. Till here, everything fine? Just convert it to quantum mechanical operator form. Okay. So now let's put it back to what we wanted to find. So we put it all the operators. Iota h cut I have taken common, and then Lx, Ly operator, Lx operator, and it is operating on some function f. So now you just do with the mathematics. So how you do the mathematics is very important. So you bring this f inside. When you sorry, f is already written with that, so you don't have to write it. F is already there. So what you do is you actually operate this second operator on f first, just like that, multiplied with f, and then the previous operator with this thing, and then you can find all the terms which are coming up. When you find all the terms which are coming up, some of them will cancel it out, very simple as that, and you will end up with some of the function which actually you can easily see this is Lz. Simple. You can do this mathematics quite simply. Is it okay?
Yes, sir.
Okay.
So similarly, you can find all the operators. But now I want you to give some homework that you need to prove L square into Lx is 0. How you do it? Any hint?
Sir, we can write L square as Lx square plus Ly square plus Lz square. Then we can use the property of
Ly square plus Lz. Okay, we write this. Then we get Lx square plus Ly square plus Lz square comma Lx equals to whatever we want to prove it to. And then we split it. Okay, we split it. Now what you can do is you can actually use a property. If there is a square of 1 and b, what you do is, sorry, this is the formula a comma b plus A comma B, A. So do you all know this formula?
Yes, Bhaiya.
Yes,
So you are,
I have a confusion. Uh,
yeah.
so sometimes A is written on the right side and that A is written on the left side. I mean, even if A square is not, if it is a product of other functions like B and C, then which formula should we use? Like both are correct or?
No, no. Let's say it is into B cap. Okay.
Yes.
A square. Okay. So then whatever is on the left will remain on left, but here it will be C cap, and here it will be C cap. Okay. So A cap went on this side first out, and then we did the computation between C and B. Okay. Now we did between A and B, and since C was on the right, so we write it down on the. It is very important that you make sure that whatever is on left comes left and whatever is on right, because the as you know that sequence matters. You are operating C first or A first, it does matter. Okay, so that you need to take care of. This is a formula. In this place now you can put C equals to A, and so this formula will reduce to A square B. Okay, right.
Okay.
So using these
Yes.
formulas you can actually find L square into Lx. If you find L square into Lx, similar, you don't need to find L square into Ly or something like that. So that you should do. With this information, let's now move forward. How to move forward? What is the next step where I want you to take you to? I am talking about operator, but it should operate on something, okay, and give you something. So let's see how these operators operate. So we give an heading, eigenvalues, eigenvalues and eigenvectors. Okay, this is something which we want to do. So let's do it. Just a second. Let's do it. Okay. Just give me a second. So now the task in front of us is, what are the eigenvalues? Eigenvalues means what you get after measuring of L square, Lx, Ly and Lz. What are the eigenvalues for them? So if we measure them, what are the possible values which we are going to get? And what are the eigenfunctions? Eigenfunctions means what will be the state of our system after we have done the measurement. So these two quantities which we want to know. So without going into mathematical detail, what I want you to tell is spherical harmonics, spherical harmonics, YLM are the eigenfunctions of L square and Lz. So can you make sense of it? Even without mathematical proof, can you convince yourself that, okay, this is not so bad, this can be true?
Yes, because L square and Lz commute.
Yes. Number one thing is both of them can have the same eigenfunctions. Number one thing is true. But for both of them, spherical harmonics are their eigenfunctions. Can you convince yourself that? So yes, see, you know, the spherical harmonic contains an information about angular momentum, and that's what we are trying to measure here. And Lz means angular momentum along z-axis, which is defined by the quantum number ml, is also contained in this spherical harmonic. So okay, it's right, it's true. So this, you don't need to prove it, you only need to remember it. Okay, so now how it operates actually? So if you operate L square on, let me write your state first. So let's say your state is A y L1 M1 plus B y L2 M2. So your state is the superposition state of the two eigenstates. Okay, so can anyone tell me now very quickly what is the probability that you will be in the state L2 M2?
So b square by a plus b, a square plus b square.
Okay, so let's say we assume that a square plus b square is 1. So the probability that you will be in the state L2 M2 will be b square. So I'm sorry, I'm repeating it again and again, but since I am assuming that most of you are new to this quantum mechanics, that's the only reason. So you are in a superposition state of the two of the eigenstates. Okay, so now let's do a measurement of L square on this state. So your L square will operate on this L1 M1 plus it will also operate on the L2 M2. Okay, so now important formula. Whenever L square operate on Lm, you get a value L into L plus 1 H cut square and you get your state back. Okay, this is a very simple and important formula which we are repeating from day 1, and I also told you that this we will study in detail in lecture 3 and 4, and that is what we are doing today. So can you tell me now what should I write in front of A now? What will be the answer if L square operates on L1 why L1 M1?
L1 into L1 plus 1 H cross square. Then again the
And
state.
right.
Y1 L1.
Right. And what will be here? L2 plus 1 H cut square Y L2 M2. So do you all understood, got an idea how your L square operates on your states? Perfect. Now let's operate LZ on your state phi. So it will operate on state L1 M1 plus B. It will operate on state L2 M2. Again, important formula that whenever LZ operates on Y L1 M1, it gives you let be LM. It gives you M H cut into Y L. So have you heard these kind of formulas before? Atomic physics or maybe anywhere?
For atomic
Guys?
bit.
Yeah, so only thing is instead of state, I'm just writing Y L1 M1. That is something new. Only thing that new is that you must have heard it in some different form. Okay, so is this the correct expression which I have written? So this is what we should know. Now, if this is what we should know, now I want you to bring to the next level. But before I bring you to next level, I need to make sure that all of you have understood each and every term till here in today's lecture. So सबको समझ आया यहाँ तक क्या हो रहा है? Now because I am going to shift to matrix mechanics.
Yes, sir.
Okay, Ayushi got idea. Everyone else यहाँ तक सबको clear है?
Yes, sir.
Any question? Any
Yes,
question
sir.
which you want to ask? If you want to ask anything till here, ask me. Then I will take 10 more minutes, and then we will write the matrix forms. Okay, so if it is clear with every one of you, okay, very nice. Now let's write the matrices. matrices of operators. In the basic quantum mechanics, you must have heard that operators can be written in square matrices. So let's write that operators are written in terms of square, not any matrix, but square matrices. And can anyone tell me how we write the states? How we write the states?
States are written as it is, right? Means the symbol that we denote them in.
No. States are also written in matrices, but which matrices?
The column matrices.
Yes. So states are, or I should write states in direct space are written states, or we can say or ket in terms of column matrix. So now if I do the bra, if I write the bra, so what is a complex conjugate of column matrix?
Row.
Matrix.
Row matrix. Okay, row matrix. So let's copy this and paste this here. So this much you know, it's a very good thing. States in direct, okay, or bra in dual space are written in terms of row matrix. So these 3 points you should know. So if operators are written in square matrix, then what is a matrix for L square? This is a simplest question which I am asking. This we will do. What is a matrix of L square then? So matrix of L square. Okay. So number one question which you should ask is, what are the dimension of this matrix? Isn't it? It is a square matrix, but 2 by 2, 3 by 3, 4 by 4, 5 by 5, what? Okay. That will depend upon what? What is the dimension of your L square matrix?
3D.
3 by 3?
Wave function, I guess.
Wave function?
Sorry, eigenstate.
Eigenstates? So it all actually depends upon your quantum number. So if quantum number is 0, then dimension will be different. Okay. If quantum number is 1, L equals to 1, then dimension is different. If L is 2, then dimension is different. So basically we will only discuss about these 3 cases. L equals to 0, 1, 2. Then by this time you will get an idea. So for L equals to 0, how many values of ML are there?
L equal to 0, 1.
L equals to 0,
M
then
equal
how
to
many
0.
values? Yeah, 1 value. So the dimension is 1. Okay. For L equals to 1, how many values of M are there?
3.
3. So dimension is 3. So for L equals to 2,
5.
5.
and for L, only L, I am not telling you L. Can you give me general formula?
2L plus 1.
12 plus 1.
2 L plus 1. So this you should remember. This is how we find the dimension. Okay, so now let's see what are the states possible. For L equals to 0, the possible state is Y00 only. Isn't it? L is 0, M is 0. But for L equals to 1, what are the possible states? Okay, 3. For L equals to 2, 5 possible states are there. Is it fine? Samjhe sab? So now let's write a matrix form for L square when L is 0. So how do we actually write this in matrix form? So the dimension is 1 by 1 dimension. So only one element will be there. So how we find actually is y L square y 0 0. Okay, this is something which we want to find, or you can write this. Sorry, this. Don't get intimidated by the formula. I am explaining what this actually tells you. But let's find this term first. L square y 0 0 will give you. What does it give you?
0.
Because the formula is L plus 1 h cut square y 0 0. Since L is 0, it is 0. Now I want to find y 0 0 L square y 0 0. I have already discussed that what you do is you take the complex conjugate and you multiply it with the whatever the answer this has came. So when you multiply the answer with 0, you again get 0. So your L square matrix when L is 0 will be 0. It's actually 0. 1 by 1 matrix. Only element is 0. Okay, so this was simple case, nothing to do with. Let's discuss L square when it is 1. So the dimension will be 3 by 3. So first element will be y 0 0 L square y 0 0. Now keep. See, how do you describe the element of the state? It is A1 B1, or you can say A12 A11 A12 A13, means this remains state 1 and this remains state 1. In the second element this is state 1, but this is state 2. So in the second element what you will do is first element will still remain state 1 L0 0. But now the question comes, what is your state 1, state 2 and state 3? So let's describe this as state 1, this as state 2 and this as state 3. Okay. Now, so what will be my state 1? I have to write the state 1 here. So 0 minus 1. State 1 here again 0 minus 1. State 1 here 0 minus 1 L square. Now here I need to write state 2. So it will be 0 0. Similarly, state 1 here. So 0 minus 1 L square. State 3. So state 3 is y 0. Sorry.
1
Yeah,
0.
0. Sorry, it should be 1. Sorry. है ना? Here I am making the mistake. Here it should be 1. Okay, 1 1. So now I need to write. This is how my matrix looks: A12, A2, A1, A11, A12, A13, A21, A22, A23, A31, A32, A33. So now I need to write second state first. So second state is 1 0. Then first state is 1 minus 1. So can you help me write this element now? What will be this element? Y. I need to write second element. So second element is 1 0.
1 0.
Second element again. So 1 0. Now this here second element 1 0 1 1. Okay. Similarly, third element is 1 1. First element is 1 minus 1. Third element is 1 1. Second element is y 1 0. third element is 1 1, L square 1 1. So do you all got the idea? We haven't calculated these terms, but these terms how we got, you got an idea. So what is the number one step? You give 1, 2 and 3 to some states. It's preferable you remain in the sequence. So ML minus 1 is 1, 0 is 2, 1 is 3. You can also reverse it. You may give it 1 as state 1, 0 as state 2 and minus 1 as state 3. Doesn't matter. Physics won't change. Then you write it the simple matrix form. So now let's calculate these terms, all these 9 terms. So how do you find the first term? First term is y 1 minus 1 L square y 1 minus 1. So can I write it like that? 1 minus 1 star and L square y 1 minus 1 will be 2 h cut square y 1 minus 1. किस किस को पता चला भाई कि कैसे 2 h cut square आया ये?
Formula से.
Simple. So Madhu, do you got the idea how I got 2 h cut square?
Yes, sir.
So these and these are orthogonal. Okay, they are the same states. So y1 minus 1 star into y1 minus 1 will give you 1. So your answer is 2 h cut square. So your answer is 2 h cut square. Fine. Now let's move on. Now let's find the second term. From the second term, you will actually be able to find 6 terms. Let's see how. Y minus 1 L square y 1 0. So can I write it as y minus 1 star? Now what will be here? Tell me. Other than Shaheen, anyone else says. What will be here? Yes, Madhu, you give an answer. What will be the answer here?
Is it 2h cut square?
बताओ भाई.
2h cut square.
Yeah, 2h cut square. Y
01.
1. Yeah, and ऊपर
0.
y 1 0. Great, very nice, very nice. But now you see these two are of different states. Y 1 minus 1 and y 1 0. So answer will be 0 because both are orthonormal states, orthogonal to each other. So answer is 0. So what core idea we get from that? If this term and this term is not same, then I am going to get answer 0, isn't it?
0.
And if this and this state is same, then I am going to get answer h cut square, 2 h cut square. Why? Because L is same for all the terms, na? L is same for all the terms.
Yes, sir.
So my L square matrix is 2 h cut square 0 0 0 2 h cut square 0 0 0 2 h cut square. So do you all agree that this will be my L square matrix when L is 1?
Yes, sir.
ओके सबको समझ आया भाई? जल्दी बताओ, पेपर में 2 मार्क का क्वेश्चन हो गया तुम्हारा.
Yes, sir.
समझे? So now any smart person tells me what will be the L square matrix when L equals to 2 without doing any much calculations. So it will be 5 by 5 matrix. But how does it looks like?
The diagonal element is 6h square.
क्या मैट्रिक्स होगी बताओ? Diagonal element will be there, but what will be the diagonal elements?
6h square. 6h cut square.
6. Great. 1 2 3 4 6 h cut square 1 2 3 1, 2, 6 h cut square 0, 0, 0, 0, 0, 6 h cut square 0, 0, 0, 0, 0, 6 h cut square. तो यही होगी मैट्रिक्स. So now without doing any further calculation, whatever L is given in the exam, can you write the matrix for L square? How this 6 came? Because L is 2. So if you put in the formula L plus 1 into h cut square, you will get 6 h cut square. So this is how it got. Matrix for LZ. So now one thing which you should remember here is nothing is changing, but only L square operator, LZ operator is coming. And how LZ operator operates, that is a different thing. LZ on YLM operates as M H cut YL. Only thing that here, so non-diagonal elements will be 0 here also. Okay. Because the previous element when operated on the initial element, it will give to you 0. Okay. For example, if I'm finding this. Okay. 1, 0. So it will be y1 minus star and L is 0. So it will be 0. Or maybe let's do is this. So H cut y1. It will give me 0. So non-diagonal elements will still give me 0. But do you think that diagonal elements will be same?
No, sir.
No, sir.
Not all.
Okay, so diagonal elements will not be same. So without doing any further or maybe much difficult calculations, let's find LZ for L equals to 1. Okay, so for the sense of completion, let's start from 0 so that we can get complete. So it will be 0. Very simple. Okay, now let's find for L equals to 1. Now diagonal elements are not same. So what will be the diagonal element for the first term? Here first term is y1 minus 1 LZ y1 minus 1. All other terms are 0. y1 0 LZ y. Is it correct to write like this? Huh?
Sir.
So now
Yes,
what
sir.
do you think will be the first element?
Sir, H cross
Minus
H.
minus H cross.
So what will be this element? Second
0.
element?
0.
0.
0. And what will be the third element?
H cut.
Sir.
Perfect. Do you got an idea how we did it? We just use this formula and then again. So this is how you write an LZ matrix. Okay, LZ matrix for L equals to 2. So now very quickly any intelligent person tells me what is an LZ matrix for L equals to 3.
Sir, the previous one was for A equal to 1.
L equals to 1. Now tell me what is for L equals to 2. बताओ भाई, very simple. You can do it in
Minus
just
2 each. Minus 2 each.
yes,
Fine.
yes, 0, 0, 0, 0, 0. Now what will be here?
Minus 1 each cross.
Very nice. 0, 0. Now here, what will be here now?
0.
Great. Now
0.
if we move forward, h cut
Plus
0, 0, 0, 2 h cut. Wow, you all are very intelligent. So done. We can write matrix for anything now. Very simple. Now let's say in the exam, LZ matrix is given, means you find out in with my technique, but in the option is this. Let me copy this. Okay, so option is this. So is this right or is this wrong?
Wrong.
No, this is also right.
So
Only
right.
difference is, yeah, only difference is we have changed the sequence of the states. Means initially we were saying this is state 1. Now what we are saying, this is state 1. So this does not change the physics, na? This does not change the physics. So this is also right. So what I want you to tell is, if whatever answer you are getting, do its complex conjugate. So if you do it, let's say for this matrix, if you do the complex conjugate, and if that matches with the option, that is also correct. Because if you will do its complex conjugate, you can do it by replacing rows and columns also. That is also fine. So always remember, this can also happen. So happen can that numbering of the states can be different, but always number in sequence. If you have given y11 as 1, then give y10 as 2 and y1 minus 1 as 3. Don't do that you give this 2 and this 3. Okay, that will be confusing. So that you should only remember. So I think I will end the today's session here. If you have any questions, you can ask. Okay. So let me stop.